Hello students, now I'll be solving some of the relevant exercises related to the concept I have discussed in the previous videos. At first, I will start with identifying whether a particular given function is increasing, decreasing, or stationary in nature. In order to perform these exercises, I'm taking help from Edward Dowling's book, chapter number 4, and I'm taking 4.3 as an example to show you the three different cases where we'll find different results after solving the problems. So, in terms of this problem number 4.3, we are basically trying to test whether the given functions are increasing, decreasing, or stationary, and also one more condition added, if it is evaluated at a particular number. Remember, this is a one-choice variable case, and as a result, you need to differentiate the function in terms of only one variable, which is x. Now let's begin. Let's see, the equation is y is equal to 3x squared minus 14x plus 5. So as you can see, x is the variable for which I will be differentiating y. So by taking the first order derivative, I get 6x minus 14. As 5 is a constant number, you know that differentiating a constant simply results in 0. Now, this y prime is definitely with respect to x you have identified here, right? So if we take that this x is equal to 4, then instead of y prime x, we can write y4 is equal to, we will plug in the value of x over here, which is 6 into 4 minus 14. The calculation is very simple over here. It is 24 minus 14, which is equal to 10, and this is absolutely greater than 0. Now, we know that if the value of the first order derivative is greater than 0, then we can conclude that the function is increasing in nature. Remember, it is increasing in nature. Okay, so this is the first problem where we have taken the decision that this particular function is increasing in nature. Let's see another example. This is 4.3b, and the function is given as y is equal to x cubed minus 7x squared plus 6x minus 2. Now, if we take the first order derivative of this function, we get 3x squared minus 14x plus 6. Again, if we replace x with 4, then we get 3 into 4 square minus 14 into 4 plus 6, which is equal to 54 minus 56. Okay, and finally we get that this is equal to negative 2, which is less than 0. That means as it is less than 0, so this is decreasing in nature. Okay, let's take a third example and let's see whether we find any different things or not. So in 4.3c, y is given as x to the power 4 minus 6x cubed plus 4x squared minus 13. Now here, if we take the first order derivative, this is 4x cubed minus 18x squared plus 8x. And if it is replaced with a value 4, then we get 4 into 4 cubed minus 18 into 4 squared plus 8 into 4, which ultimately provides us with 256 minus 288 plus 32, or it is actually 88 minus 288, which is equal to 0. Now, if the value is exactly equal to 0, that means the function is stationary in nature. Okay? It is neither increasing, it is nor decreasing. It is simply stationary in nature. Let's move towards another example. Now we would look at the second order condition as well. In the previous video, if you remember, I have talked about the necessary and the sufficient condition. So here we will basically check both, and we would try to identify whether the function is at its relative maximum or minimum, whether it is concave or convex in shape. So we are taking problem number 4.5 from the same chapter and focusing on problem 4.5a. The given function is negative 7x squared plus 126x minus 23. If we take the first order derivative, we get negative 14x plus 126. Now here, no particular value for x is given. That's why we need to set this first order equation equal to 0. And then we need to identify the critical value for this particular first order derivative function. Okay, so from here we can get in other ways 14x is equal to negative 126. So negative and negative over here crosses out, and we are left with x is equal to 126 divided by 14. And it eventually provides us with 9. So over here, basically, x is equal to 9. Okay. Now let's take the second order derivative. If you remember, the first order derivative f of x is equal to minus 14x plus 126. Now if we take the second order derivative, we will get a negative 14, which is less than 0. Okay, so automatically, if the second order derivative is less than 0, that means the function is at its relative maximum, first of all. And if it is at its relative maximum, that means it is concave in nature and shape. Okay, so that's what we get from this particular example, that the function is at its relative maximum and concave in shape. And also remember the first order derivative where x you have identified 9. Now, if you plug in that value in the given function, what was the given function? F of x is equal to negative 7x squared plus 126x minus 23. And by solving the first order derivative, we got x is equal to 9. Now you can always evaluate your given function at this critical value to identify whether the function is increasing or decreasing in nature. So over here, instead of x, if you put 9, you will get minus 7, 9 square plus 126.9 minus 23, or negative 567 plus 1134 minus 23, which is equal to 554 greater than 0, and representing that the function is increasing in nature. However, for this particular problem, my focus was specially towards whether the function is at its relative maximum or minimum. But you can also identify whether the function is increasing or decreasing in nature. Now, let's take a last example under this particular lecture video. This is also to identify whether the function is at its relative maximum or minimum, and how does the value or the result changes as we change the critical points or the critical values. So let's take, this is 4.5b of chapter 4, the same chapter. So f of x is given as 3x cubed minus 36x squared plus 135x minus 13. Sorry, my bad. I will actually refresh this and will write it for you again. So this is 4.5b, and the function is given as f of x is equal to 3x cubed minus 36x squared plus 135x minus 13. If we take the first order derivative, we get 9x squared minus 72x plus 135. Let's make the equation a little simpler. We can take 9 in common, so there is left x squared minus 8x plus 15, which is equal to 0. Okay, let me clear this part a little more. Writing into a new device, sometimes it is challenging, and sometimes it is getting difficult, but I'm trying hard. Let's see. Yes. So here, then this is equal to, I said, x squared minus 8x plus 15, yeah, set it equal to 0 again. Okay, or this is x squared minus 3x sorry, I'm making a mistake over here. Let me check again. Okay, let's do it again. This particular line. Okay, so you know, if I take 9 to the other side, 0 divided by 9 will provide us with a 0? Yes. So here we are left with x squared minus 8x plus 15. And this is equal to 0. Or we get x squared minus 3x minus 5x plus 15 is equal to 0. Okay. Now if we take x in common from here, then we will be getting, if I take x in common, yes, so if I take x in common, I will get x into x minus 3 minus 5 into x minus 3, set it equal to 0. Or I get x minus 3, x minus 5 is equal to 0. So in such way, x is either equal to 3 or it is equal to 5. So we got two different critical values, okay, after solving for this. Now, with these two critical values, we will be performing the sufficient condition. That means the second order condition. Okay, if you remember, the first order condition was f prime x is equal to 9x squared minus 72x plus 135. So in that case, the second order would be 18x minus 72. Okay. And now if I plug in 3, then I get 18 into 3 minus 72, which is 54 minus 72, which is negative 18 less than 0. So the decision comes at relative maximum, and let me write it again, relative maximum, and it is concave in nature. Okay, but in the second order derivative, if I put 5 and multiply it with 5, then I get 90 minus 72, which is equal to 18. Now this is a positive value, and this value is providing me with a different decision, which is showing that it is at its relative minimum and it is convex in shape. So I have chosen this particular exercise just to show you that how, depending on the value of x, basically the decision changes. The same very given function, while evaluated at different points, they will be providing us with different results or conclusions. I think I have covered the very basic category of problems that I actually need to show you for your better understanding of the concept. In the next lecture, I'll be moving towards some economic applications, and will try to enrich your knowledge with the understanding that you have built so far on optimization and in terms of a single variable. Thank you for watching. Please go through the video carefully again, and please excuse my bad handwriting as I'm actually facing difficulty in writing this particular device, but I hope I'll be expert as I proceed. Okay, thank you so much.